Hi, everyone. This week, we're going to start talking about hypothesis testing. To me, the most frustrating part of learning statistics as a student was that my professors kept mentioning concepts and then saying, well, we'll talk about that later, or this is relevant now, but I can't really explain it to you because you don't have enough information. To me, statistics is a frustrating subject your first time learning it because the pieces don't start fitting together until you get a holistic view of all the parts. But you can't look holistically at the parts until you know what they are individually. In this lecture, you're going to see a lot of concepts that you've read about or heard me talk about before. And finally, we're going to get to start talking about what they are and what you do with them. In any exploration of data, whether we explicitly state it or not, we really have two hypotheses. The first is the null hypothesis. The null hypothesis, which is represented by H0, is that the status quo maintains. For example, let's think of a textile company. And this textile company believes that there is at least 1,000 feet of string in every square foot of their fabric. The null hypothesis for that company would be that no matter what sampling of their fabric you pick up, you will find that there is at least 1,000 feet of string in each square foot of fabric. The alternative hypothesis is that the status quo does not maintain. If the null hypothesis is that there will be at least 1,000 feet of thread, the alternative hypothesis would be that there would be less than 1,000 feet of thread. Between the null and the alternative hypotheses, all possible outcomes are indicated. The null hypothesis always assumes a population parameter. In this case, the company would assume that they know the minimum amount of thread for absolutely all of their fabric everywhere throughout the company. And the null hypothesis is always the hypothesis that includes equality. The null hypothesis is that your value is exactly equal to, or it will be that it is less than or equal to, or greater than or equal to. The alternative hypothesis can be that a value is not equal to, that a value is less than, or that a value is greater than. There are two ways that you can test hypotheses in a single sample. The first option is by looking at the critical value, and that critical value uses a tool that should be abundantly familiar to you at this point. Here, once again, we see a normal distribution curve. We see that negative 1.96 standard deviations is marked to the left, and positive 1.96 standard deviations is marked to the right. In single sample hypothesis tests, we're always making hypotheses about a mean, that the mean is equal to, greater than or equal to, or less than or equal to. Using a critical value method of single sample hypothesis testing, if we know the standard deviation for the population, we transform our mean into a z-score. And then we identify whether or not that z-score is less than the lower critical value of negative 1.96 or higher than the upper critical value of positive 1.96, assuming 95% confidence. Remember again that we believe that 95% of our values fall between negative 1.96 and positive 1.96 standard deviations from the mean. That means if we find a sample whose mean falls outside of those bounds, it's either has a z-score of less than negative 1.96 or greater than positive 1.96, then we have found something that is different from what we know 95% of the population should look like. In that case, we believe we have found something different, something unique, and we say that that mean is statistically significantly different than the mean of the population. Now, if we don't know the standard deviation for the population, we can use this exact same type of test, except we'd be using a t-distribution rather than a normal distribution. A couple more reminders from previous chapters. We get to set our level of significance. So here, we're assuming 95%. Depending on how important our confidence is, we might want to set it lower, such as 80%, or higher, such as 99%. When you change your significance values, your critical values for what your cutoff is also changes to be consistent with your level of confidence. Also, as we've discussed before, we can never be 100% confident with statistics. In statistical analyses, we always run two different types of risk. The first one is a type 1 error. A type 1 error is something that would occur if you ran your test, you found that there is a statistically significant difference, but as it turned out, that difference only occurred by chance. Think of a type 1 error as a false positive. Perhaps you go to CVS and you buy a test for an illness such as COVID, and you get a false positive on that test. That's a type 1 statistical error. As you've seen in previous chapters, your level of significance is represented by the Greek letter lowercase alpha. Alpha is literally the probability that your test will result in a type 1 error. When you set your level of probability, you are the one who determines what your level of alpha is that you're willing to risk. And again, that's based on how certain you need to be. The second type of statistical risk is the type 2 error. Imagine again that you've gone to CVS and you've picked up your test and you get a false negative. You actually have the illness, but that testing unit missed it. That would be an example of a type 2 error. The probability of a type 2 error is always represented in statistics by the Greek letter beta. You don't get to set a beta level after you've set your alpha level because your beta level is what's left. It's a balance. Alpha and beta continuously balance one another out. The better your probability of alpha, the worse your probability of beta, and vice versa. The better your probability of beta, the lower your probability of alpha. This is why we can never be 100% confident in our results. Now, I have a little trick to help me remember the difference in type 1 or type 2 error. I don't know if any of you were fans of Winnie the Pooh back in the day or you are right now, but there's a character in Winnie the Pooh named Tigger who is very helpful in sorting this information. Tigger always used to say to Winnie the Pooh, TTFN, ta-ta for now. TTFN means ta-ta for now, or type 2 false negative. So if you ever get confused about which is which, just think of our friend Tigger. Now, I said there were two ways of doing these single sample hypothesis tests. The second is using p-values. We've seen p-values before. Remember in SPSS when you would get a significance level on your correlation? That was a p-value. Your p-value is the calculation of the probability of getting a test statistic that is equal to or more extreme than the sample result. When you're using p-values, if your p-value is less than alpha, then we reject the null hypothesis. Again, as we've discussed before, most businesses want to be 95% confident in their results. So they use an alpha of 0.05. If we're using p-values to test our hypotheses, then we determine whether or not we fail to reject the null hypothesis or whether we reject the null hypothesis based on whether p is less than 0.05. Now, there's one more thing about single sample hypothesis tests that you've heard about before, but we can only really discuss now, and that's this notion of a one-tail versus a two-tailed test. Think back to the tables we've looked at. Remember how we had cumulative probability, one-tailed and two tails? Here, finally, you know what to do with them. When we're using a t-table for one-tailed hypothesis testing with a critical value, we're going to be looking for degrees of freedom and then either a one-tail or two-tail value. Which one do we use? Well, that depends on what we predicted. If our null hypothesis is simply that our mean is equal to a value, so if my null hypothesis is that student GPAs are equal to 3, then I'm going to be looking at the two-tailed value associated with my level of confidence. If instead my null hypothesis is a greater than or equal to, so if my null hypothesis is that student GPAs are greater than or equal to 3, or student GPAs are less than or equal to 3 on average, then I'm going to be looking at a one-tailed test. Let's look at how you run these analyses in Excel and SPSS. Here we have that data set we looked at several times on faculty communication in SPSS. Remember that we said computer-mediated immediate behaviors were good email practices that instructors may use. I'm going to hypothesize that faculty computer-mediated immediate behaviors are greater than or equal to 4. So students would assess them at least on a scale of 1 to 7, greater than or equal to neutral. To do this, I'm going to go to Analyze, Compare Means, One Sample t-test, and of course we don't have a one sample z-test because SPSS is going to be conducting the test based on the standard deviation it calculates itself. I'm going to go down and get my computer-mediated immediate behaviors variable, and I'm going to set my test value to be equal to 4. And then I'll hit OK. Here's my output. It tells me that I have an N, which is a sample size of 334, that my mean within the sample is 5.7, with a standard deviation of 1.1, a standard error of 0.06. Now for the test. My t-value is 28.29. I have 333 degrees of freedom. And then here is where I'm really interested in what I'm looking at. Because my hypothesis was that the value will be greater than or equal to 4, rather than simply equal to 4, I'm looking at a one-sided p significance test. The default is 95% confidence. I could change this if I wanted, but I'll have no reason to ever do that in business. Because my p is less than 0.05, I am confident that in this sample, the mean is statistically significantly greater than 4. Now let's check it out in Excel. Here I've copied and pasted my values from SPSS and I've given it a column header. Doing a one sample t-test in Excel is a little tricky because Excel isn't actually designed to do it. You have to lie to Excel and trick it to do it for you. So the first thing I need to do is set up a dummy column of data. Your dummy column needs to be filled with zeros, and Excel will actually let you do the analyses with only 2 lines of data listed. So this is enough. Now I can go into my tool pack. I can scroll all the way down to t-test. And here I'm going to select t-test to sample assuming unequal variances. Something important here is to do this properly in Excel, I'm going to need to include the name of the variable in my range. So for variable 1, I select everything in column 1, including that computer-mediated immediate behaviors header. For variable range 2, I select the header dummy and the 2 zeros. Here for hypothesized mean difference, I'm going to input 4. The alpha again comes preset to 0.05, and the output range, I'm going to tell it that it can start printing information in D3, just because. All right, there's my output. I'm going to clean this up to be a little more honest. I'll get rid of the dummy data. And I'll change this to a 1 sample. Now, what did I learn? And more importantly, how does it compare to SPSS? Well, Excel says that my mean is 5.7. SPSS agrees. Excel doesn't give me a standard deviation. Instead, it gives me a variance. Well, how do I get from standard deviation to variance? I square standard deviation to get variance. So if I take the square root of this variance value, I actually get the standard deviation value that I was given in SPSS. Our hypothesized mean difference here is set to 4, which was our test value set for SPSS. Our t-stat, 28.29, same on both sides. Our degrees of freedom, 333, same on both sides. Here's the difference though, and it's not a difference in actual results so much as difference in presentation. Excel is giving you your exact p-values in scientific notation. So this is 7 e to the negative 91, which means that if we were going to write this out longhand, it would be 0.91 zeros and then 7. SPSS just summarizes by saying it was less than 1,000. It's really low. So it's the same output. It's just that Excel gives you the exact output in scientific notation, whereas SPSS says, here's what you need to know. But both programs agree that the mean of this sample, looking at the two-tailed t-test, was different than the mean hypothesized. I hope this helps you see how all these pieces are starting to come together. If you have any questions, don't hesitate to reach out.